So lab has started. There's a few clarifications for the lab. If you read the document, there's 3 sections, right? So there will be 3 weeks of when you'll be doing certain things. And although we're going to have the lab report due on the 31st of March, that's kind of described at the end. That's kind of after the midterm, so it's about 10 days or more after you really complete all your work. I'm giving you that kind of leeway just so you don't have to type in the lab report as you're studying for midterm. But really, this means that there's no lab work in the lab during that time. So it's just report writing. So you need to be checked off to have like completed lab work and you have all the measurements done the week the lab's due. And that's on the syllabus. So that's the, I think what we can take, you can take a look. So there's 3 consecutive weeks. And that time you should get checked off by Alberto in the lab that you've completed these sections. Because we don't want like during spring break makeups in the lab trying to do something just so you can write the report. But the report writing itself you can leave after the midterm so that you can use your time to really review the material and study. Okay. Posted some clarifications last night regarding the homework on Piazza. Hopefully people got that. If not, check Piazza before you get to do the problems. And one is just kind of a hint how you should do this small signal analysis a little bit more kind of intuitively rather than cranking out KVL, KCL for the supply sensitivity. And another one is just the sizing clarification for problem 1. That should help you kind of avoid weird regions of operation. Okay, today we're going to talk about or continue the differential pairs. We started last time looking at the bipolar, just so you can get ready for the lab. So we looked at bipolar straight with a very narrow range of kind of input voltages that it can get, about 6 VT. And then we added the resistive degeneration in the emitter to be able to expand that input range. Of course, then you're trading off the gain. For that, and today we're going to kind of formalize the differential amplifier concept and do the MOSFETs. So that will be sort of more as to what you would do in integrated circuits with these. So if we look at the differential amplifier, in general, and you've seen this sort of many times before, but we're just going to abstract it as a block that has 2 inputs. And in this case, I'll just draw 1 output, but we'll soon see that actually there are differential input, differential output amplifiers, or differential input, single-ended output amplifiers. So we'll be able to characterize all this. So in this case, quantities you care about is that the output voltage is proportional to the difference of the input voltages. And we call that proportional factor the differential mode gain. And then we have the common mode gain, which is proportional to the common mode or the average value of the 2 input voltages. So the definitions that we'll use are sort of that VID is VI1 minus VI2, and that VIC, which is the common mode input, is the average. So what we want in this type of system is, so our circuit is, we want large ADM and small ACM. The reason is, as we'll see later, is that this common mode variation usually comes from things that you don't want, like supply, for example. So supply fluctuations or noise will map directly into all the biases, all the voltages moving kind of the same way or in a similar way. And these things you want to reject as you're moving from one circuit stage to another. And to that context, we're also going to be looking at something that we call common mode rejection ratio, which is sort of the absolute value of ADM over ACM. And we sort of covered that a little bit in homework 1, but at sort of a ideal op-amp kind of based circuits. We're going to be calculating this now on kind of transistors. So just like we did for bipolars, let's take a look at the sort of the CMOS diff pair. And then here we'll, just for simplicity, say this is ISS. And we'll say that through M1, we have current I1, and you'll have current I2 through M2. And then we'll say that delta I is really I1 minus I2, and VID will be our VI1 minus VI2. So just by writing the MOSFET equations for this, for M1 and M2, we have that I1 is K prime over 2 W over L. And then here we'll just say, okay, some VGS1 minus VTH square. So we're making some assumptions. Let me just clarify them here. So one is that M1 and M2 are in saturation. Two is that M1 and 2 are identical. 3, we'll neglect the body effect. And oops. 4, we're going to neglect our output conductance. So this is just to very simply derive kind of the DC transfer function. So we'll write that I2 is K prime W over L, VGS2 minus VTH squared. And now, if I go and look at the KVL between the input 1 and input 2, I'm really going VI1, VGS1, VGS2, and VI2. Right? So I have that loop. So I can say that VI1 minus VI2 is equal to VGS1 minus VGS2. If you go around this KVL loop. And this really is, by definition, the differential voltage. Now, because we assume that the transistors are the same size, VGS1 minus VGS2 will be just the difference in the overdrives. Right? So I can write that VID equals V overdrive 1 minus V overdrive 2. And then this would really be then the square root of the currents divided by this sort of factor of let's write it nicely. Right. So this will be kind of the common factor. Now, this relates the VID to the square roots of the currents. If I look at the KCL, and KCL would again be I1, I2, and ISS. So the ISS has to be the sum of the two currents. So ISS has to be equal to I1 plus I2. If I go and solve by So if I go and solve by I1, what I'm really getting here is that I2 is ISS minus I1. I can take that and plug it in here. And then I get essentially a quadratic equation by I1. Okay, so if I solve that explicitly, just like we did sort of for Wheeler sources and things like that, you're going to get that I1 is ISS over 2. There will be two possible solutions, but only the plus is kind of meaningful. And then we're going to have VID and the square root of 4 ISS over K prime W over L minus VID squared. And correspondingly, I2 will be ISS minus K prime over 4 W over L VID square root of 4 ISS. So if I subtract the two, then I'll get that my delta ID, or delta I, is equal to K prime over 2 W over L VID, and then the square root. What is interesting about this formula over here is that you see it actually, this delta I actually depends on VID here. Or in other words, unlike in our case previously where we had in the bipolar case, our difference in current was very, very narrow. We very quickly reach the total ISS, or the tail current swings. Here, I can sort of, by biasing the MOSFET, I can sort of stretch out that region. Okay, so let's draw how this looks like. So if I'm, and you'll see what I'm talking about. So if I'm plotting delta I, just like we did last time, for bipolar versus VID, let's say we'll get, goes through 0, the max value, the min value will be ISS, right, and minus ISS. These happen when I switch all the currents to flow through one of the transistors, right? And then in this range over here, I'm going to get different curves. I'm not drawing too well. Okay, but and all these are going to essentially depend on the V overdrive. So, for example, if we pick a point and we say, okay, well, here where I'm close to ISS, I'm going to call this point VID off. This is the point, oops, I don't know what's going on. This is the point at which sometimes things behave. This is the point at which the output current no longer depends on the input delta, right? That's the point where we said we're kind of saturating the input. And we can only work in the input range until this cutoff point. So this VID off, we can look at the equation for VID and say that really happens when one of these currents is 0. When one of these currents is 0, I'm switching all the current into one of the two transistors in the differential pair. Right? So the way we're going to define this VID off then is exactly that. So this will be, if all the current is flowing through one transistor, then that current is ISS. The other one is 0. And then we have this K prime over 2 W over L. So if you look at this, this is really V overdrive times a square root of 2. And this overdrive is really VGS minus VTH when VID equals 0. So I'm talking about the overdrive not when you're fully switched. Okay. Talking about the overdrive when each of the transistors conducts ISS over 2. Right. So, and I have no differential voltage applied. So I just have bias at both inputs. At that point, this overdrive would be a square root of ISS over 2 over K prime WL, right? Okay. So you see from this factor over here that this is really our VID off. Right? So VID off is proportional to a square root of ISS and K prime over L. So by tweaking what this is, I can essentially expand my region of operation. And if that's the case, then I have essentially a similar behavior to that of a resistively degenerated bipolar transistor. Okay. So I have another knob with which I can sort of expand this range. So some of the key points. If you take a look at the formula for delta I, if VID is small, then delta I is proportional to both VID and a square root of ISS. So you can use this type of circuit to do multiplication between the input differential voltage and something that is in the tail. And this is often used a lot in, let's say, circuits like mixers or GMC multipliers, etc. So you'll do that kind of in more advanced courses. But this is one of the features of the differential pair. The second one is obviously that delta I is between minus ISS and ISS. Those are the swings, currents you can swing. The third one is that that we mentioned, that VID off, which is this cutoff range, is a function now of WL, of ISS, etc. This has not been the case in bipolar. Okay? In bipolar, your input range is 6 VT, and there's nothing you can do about it unless you stick in a resistor there. Here, you can tweak the sizes, you can tweak the bias current to make that input range what you need it to be. Okay. So again, like the fourth would be that the input range is square root of 2 times the V overdrive at VID equals 0, right? And that is different than 6 VT in bipolar. Or I should say greater. Okay. 5 is essentially that this is similar to BJT with emitter degeneration. as you can guess, the transconductance of the diff pair is somewhat related to GM in some way, right? And we'll see actually that it's a pretty simple relationship that we're going to derive. So let's take a look at how to do that. So far, we've sort of only seen how the current gets switched, but obviously you want the voltage at the output. So now you have to decide what you want to load this diff pair with, right? What types of loads did we look at so far? Did we have resistors as loads? Yeah. And what else? Current mirrors. So we had active loads. We had also diodes as loads, right? So we had a whole bunch of different things that we could load this thing with, right? And people actually do that in practice. So here we're going to first take a look at what happens if we load the pair with resistors. So this would be kind of, well, I'll add here some RSS, which would be kind of the output resistance or output impedance of the current mirror, or this current source we're going to call ISS. Just because in practice we really don't have infinite resistance current sources. Right? We don't have ideal current sources. There's, as you've seen with all that we've done, you can get them to have pretty high output resistance, but still it's finite. So for this type of circuit, notice that we have now 2 inputs and 2 outputs. So both VO1 and VO2. So we're going to, in the most general sense, say that, okay, well, VO1 is A11 times VI1 plus A12 times VI2. VO2 is A21 times VI1 plus A22 times VI2. Now, this means you could be doing superposition to solve. So you ground VI2 and you drive it with the VI1. I'm talking about small signal analysis. But usually, this doesn't really give you much intuition about the things that you care about, and we care about differential gain and common mode. So we can do a decomposition here by just simply changing the variables. Okay. So we're going to say that VID is VI, sorry, we'll do this lowercase. VI1 minus VI2. Say that VIC is VI1 plus VI2 over 2. VOD is VO1 minus VO2. And VOC is VO1 plus VO2 over 2. Okay. So if you do this, then you can kind of represent this same thing by doing a different drive. So here I'm going to have first VID over 2. And then on this side, I'll have minus VID over 2. And then as a common component, I'll have my VIC. If you do the math, so you're essentially adding to VIC, which is the average, you're adding half of VID, you will get VI1. Just if you halve this and then sum, these will cancel out, and you'll get VI over 1 over 2 plus VI1 over 2. So that's VI1. On the other side, you'll get VI2. Okay. So the nice thing now is that I can rewrite the equations, but to say that VOD is now ADM. So instead of this A11, A12, times VID, plus I'll have a term that is ACM to DM. So this is common mode to differential mode conversion, times VIC. And then VOC will be a differential mode to common mode times differential input, and then the common mode times the common mode input. Okay. So through various techniques, we're going to be able to figure out what ADM is and what ACM is. And then if you look at kind of imperfections, diff pairs with imperfections, or not really completely symmetric diff pairs, you'll be able to get the other components as well. And we'll do that in next few lectures. Okay. For now, in balanced case means all the transistors are identical, etc. Both of these, that we get that ADM CM equals ACM DM equals 0. Okay. So let's go and do the small signal and see how we can analyze this. So we'll use, of course, superposition. So as a first step, we're going to say that VIC equals 0. So this is, we're looking for differential mode. So ADM is what we're looking for. So now in this case, if I simplify the schematic I've showed, what we have is VID over 2, GM VGS1, RD. And then here we have again GM VGS2, RD, minus VID over 2. And then over here, for now, I'll keep this RSS. But we'll see in a moment we don't really need it. So VGS1 is, so let's label this VS. So this is VGS1, and this is VGS2. Can also label these currents as I1 and I2. So if you take a look at this situation over here, I can go and start solving this in terms of nodal analysis. And pretty soon I'll be able to come up with some answer. Okay? But I think it's worthwhile analyzing this circuit because of the symmetry. You have perfectly symmetric left and right side, and you have kind of anti-symmetric input. Right? So circuit topology is symmetric, but the input voltages are the opposite sign. So the question is what really happens kind of in the middle of the circuit. Right? There should be some balance that's set up as the two sides are moving left to right. The intuition says it's like a seesaw. As things are moving, the middle is staying the same. Right? So I could make an assumption that as these two voltages are the opposite sign, then my Vs equals 0. Okay, so let's see if that assumption can hold. Okay? So if Vs equals 0, then VGS1 is just VID over 2. Right? VGS2 is minus VID over 2. So all the current that's generated here really is flowing just up here. Do people see that? So if Vs equals 0, VGS1 equals minus VGS2. So VID over 2, right? So therefore, I1 equals I2. So if this is true, then there's no current flowing through RSS. If there's no current flowing through RSS, what's the potential of at Vs? Okay. So I RSS equals 0, and therefore Vs indeed is 0. Okay. So if Vs is 0, for all intents and purposes, when I'm analyzing this, I could ground this point. Right? So really, this circuit now becomes, I'll label this VO1 and VO2. So this circuit now becomes a simpler circuit. Okay. And my output is here. So from this, what is my ADM, which is VOD over VID? Yep. It's minus GMRD. Notice that I've skipped a step here, right? From this circuit, we can only figure out what is VO1 over VID over 2, right? Which is minus GMRD, right? But then VO1 is only a half of VOD, right? Because VOD is really a difference of VO1 and VO2. So VO2 would similarly be over minus VID over 2, will be minus GMRD. So when you add the two, you'll essentially get VOD over VID, because VOD, we said, was VO1 minus VO2. Okay? So the gain is the same simply because we get a half of the voltage to produce half of the output. So the gain is the same as if we took the full voltage and produced the full output. Okay, so this is differential. Okay, let's take a look at what happens when we do the common mode. In this case, VID equals 0. And we are looking for ACM. So in this case, we have VIC on both sides. And then here we have the same thing. Now I'm going to, just as a trick, I'm going to split this tail into two. Again, this is VGS1, this is VGS2. Regardless of whether I split this or not, okay, as I'm moving these two simultaneously up, what's happening with this node Vs? It's also going up, right? Is this part of the, is this voltage any different than this voltage? No. So the currents are the same, resistors are the same, everything is the same. So essentially, because of that symmetry, what's happening is that Ix equals 0. Essentially, there's no imbalance in this circuit that would cause more current to flow through this right half than through the left half. Simply because everything is kind of driven the same way. And everything is identical. In other words, you may say that, OK, I get I1 here and I get I2 here. Because VGSs are the same, then I1 equals I2. If these are equal, then to create the same voltage, they must be going through two identical resistors, right? So one will flow to 2 RSS, the other one will flow to another 2 RSS. So I1 will flow here, I2 will flow here, which means that Ix is 0. Okay. So if Ix is 0, I can essentially go in and take out this branch. So then my half circuit would be something like this. Okay. And then from this, my ACM would be what? So it would be minus what? GMRD over? Right. Now, if I really wanted to sort of include body effect and stuff like that, I could say, okay, well, this is plus GMB and stuff like that, okay? Because this source is not really at ground, right? So I could do that, but for this type of analysis, we don't need to do that right now. But this is kind of the common mode gain. Okay. Notice that we've here calculated expression from VIC to VO1, right? ACM is defined as VOC over VIC, right? But remember that VOC was the average of VO1 plus VO2 over 2. And in this case, VO1 is actually equal to VO2 because you have the two identical subcircuits, right? The other half is the same. VIC drives the same identical circuit, right? So VO2 is equal to VO1, and their average is equal to both VO1 and VO2. So from this, I can calculate just this gain, and it will be exactly the same. Okay, make sense? Okay, so these two will hopefully won't do this exercise again, because this is just to prove to you how these circuits can be split. But in reality, what you would do if you just analyze these things is you would essentially go and say, well, I'm going to follow a certain procedure, right? And we'll say, we'll name that procedure, let's say small half circuit or bisection analysis of balanced circuits. So balanced is key. If it's not balanced, you can't apply these concepts. You have to look for where the mismatch is. So we're going to first do sort of draw schematic. And see the balance. 2, we're going to use superposition. That's what we just did. We turned off VID, then we turned off VIC, and we looked at what kind of symmetry we have, right? And in this superposition, we're going to have, so apply differential mode input and simplify schematic. So by simplify schematic, what I mean is what we did was we grounded the tail, right? Because we saw that if we apply differential mode input, we can actually get that point to be 0, and then we can cut the circuit in half. For B, as we do the same thing for common mode and simplify. And then C, of course, is add the two together. Okay. So real quick, let's do it without doing small signals, right? We're just going to go and say, okay, I have my diff pair. I have my ISS and RSS, so I'm just going to draw them as ISS over 2 RSS, and then again a symmetric thing over here. RD. Okay, so on one end, I'm applying a superposition of VIC plus VID over 2. And on the other hand, I'm applying VIC minus VID over 2. So as we said, in 2A, if we apply a DM differential input, then VIC is 0. I ground this node, so the circuit I'm getting is just this. Okay. And differential gain, I don't even need to write small signal model. I know it's minus GMRD. For 2B, I'll cut this. I'll cut this node because there's no current. And then I get 2 RSS, RD, and my output is here, and then VIC, VO1 is here. So then I get my same. So this is all by inspection. I'm no longer doing small signals. That's how you should do it. Okay. So from here, what is the common mode? Yep. Or in this, we can also add the GMB factor. Here I can also put just. Yeah. Okay. So how else can we load if we don't want to use resistors? How else can we load the diff pair? Active? Well, there's several ways. So let's do active one. One would be with what? If you load it with diode connected device, right? Then that would be the same, from small signal would be the same as a resistor, right? It would be like 1 over GM, right? So in that sense, the same exact analysis that we just did for resistive loaded applies, right? It's just the gain will be very low. It will be GM times 1 over GM, right? So if you want higher gain, you need to load it, what? You can load it with cascode, or you can even load it with just a transistor in saturation, right? Because then the load is R0, right? So just like we did on a single stage, right? Remember we had something that was something like this, right? And then this was biased from somewhere else, okay? So we had a single stage, so that we did last lecture, I believe, was something like this, right? This was a single stage where this PMOS is just loading this NMOS with R0, right? So your total output, so you're seeing RO here, you're seeing RO here, right? Or say RON, ROP, right? So total output was RON in parallel with ROP. So now we can do the same trick with the differential. And so what you would have is keep this biasing circuit. And then over here, generate two loads. Here we'll have to put I over 2, just because I'm mapping to each branch, right? Providing a reference for each branch. Nominally, when my input is not changing, I/O over 2 should flow through each one of these. Okay? Oops. Just real quick do this so we don't run out of juice. So in looking at this, can anybody tell me what is the differential gain? So my outputs are going to be here and here, right? So this is my VOD. Anybody has an idea? Okay, so you're saying it will be minus GM times some R0. So roughly RO divided by 2 if we assume that these two have the same R0, right? Okay, so same lambda, okay. But it will really be kind of ROP in parallel with RON. Or we could say this is M1, M2, M3, M4. This will be minus GM 1 times RO1 in parallel with RO3. We're assuming M3 and 4 identical. Okay. What's the problem with this circuit? It's not really, I mean, it's not really different than, well, this, I haven't really said that this I/O has some impedance, right? So, in fact, if you don't have it, then your common mode gain will be 0, right? Because RSS will be infinite, so the bottom. The problem is going to be that these two sources have to be exactly matched. right? Because you're relying on the fact that this source over here will replicate down to exactly I over 2. So that in the just biased case, before you apply any differential input, you have the two summing together into I naught. And obviously, even if the matching from here to over here is exact, these two would have to be exactly in 1/2 relationship with respect to each other, right? And that's not easy to ensure. So what you would want to do is go to something where it's kind of more like a self-biased concept that we talked about earlier in biases. I'd like to have just one source and not have to rely on the second one providing the biased matching. So anybody have an idea how I can do that? What did we do when we did the self-biasing? What did we use in the top over here? We said at the bottom was a source, and at the top was what? We drew these two boxes, like there was a source, current source, and then there was something here, and there were currents going like this. Current mirror, right? Okay, so same thing here. What you'll have is your diff pair, and then over here we want to mirror the current from one side to another. Right? Okay. So if in the case where there's no input, differential input, so let's say if we have VIC on both sides, I have IO over 2 here, and that's mirrored to IO over 2 here. So that is a possible solution, right? Okay, so this thing, it has this kind of imbalance over here, in a sense that the load is different, but you can still, if you look at the tail, what's happened at the tail, if you're neglecting kind of R naughts to the first order when you're looking at current distributions, because it really GM is, 1 over GM is so much smaller, you can kind of apply the same bisection principles that we talked about. I'm not going to split apart the whole circuit, but what I'm going to do is I'm going to be able to say that, hey, if I have a differential voltage here and a negative differential here, I can sort of assume this is grounded. And if it's grounded, then I can do superposition from, because in this case, I only have this one output, VO. I can do superposition from this input to this output while this guy is grounded. And I can do the other thing vice versa, right? So with these, you will, in the next class, we'll sort of do a quick derivation for the differential gain and common mode gain. But just keep in mind that you can sort of still play these bisection tricks to a certain extent if you really analyze what's happening with currents. Okay? Good.